So I'll get started. Welcome, everyone. It's my pleasure to introduce Jing Xu. You should know that she's a new member of our community around here, just started a lab at the University of Georgia. And I met Jing when she was a graduate student at UC Berkeley in the Department of Psychology, working with Rich Ivory and Tim Griffiths. So she has a very strong cognitive and cognitive motor background. And then ran into her again at Johns Hopkins when she was working at John Krakauer's lab in stroke rehabilitation. And John's also spoken at this series, so that's a great combination of skills. And I look forward to her sort of participating in our community moving forward. So please reach out to her. Some of you may know that she helped out with our deep lab cut and motion mapper tutorials. So welcome, Jing, and take it away. If I'll just say I'll monitor the questions in the chat for afterwards, and Jing, you can tell us how you'd like to handle them if they come up during the presentation.
Thank you, Lena, for the very nice introduction. So let me share my screen here. Okay, thank you everyone for inviting me to give this presentation. It's my great honor to join you today. I'm very excited to meet everyone in your dynamic group. And a little bit about myself. I just joined UGA last July. I'm very excited to join your community and seeking for exciting collaborations. My research program focused on human dexterity, especially investigating the behavioral and neural mechanisms of a skilled movement, and also try to answer some rehabilitation questions of how to restore skilled movement after neuromuscular injuries. So today I'd like to share some of our recent findings in dissecting human hand dexterity and then recovery processes after injury. So it's getting close to the lunch time. I guess you're probably already thinking about what you're going to have for lunch. So I'd like to share a quick video clip here. But when you are watching, I'd like you to focus on all the different things the hand is doing. Be careful, you might want to adjust your volume here. Okay, so So we all know that a skilled hand is critical in our everyday life. And this is a little video clip of Alvin Joe's Tasty. It's on Facebook, already hit 1 billion views by last May. So millions of people watch it. When they watch it, they watch the food. But when I watch it, I watch the hand. So, but we know that after injury, a skilled hand can be, detrimental to our everyday life, and especially seriously affecting our everyday quality of life. So, what I'm going to share, another one is a little video clip that we collected in our study of stroke hand function recovery. So when you watch it, I'd like you to focus on the huge contrast between the good hand on the right side and the impaired hand on the left side. You don't see his face, it's covered here, but if you see his face, you can see that he was struggling so much there. So this problem urges us to really understand what's going on here. And the reason I study the hand is that using stroke and injury is twofold. Scientifically, it gives us unique opportunity to really understand the mechanistics of the motor skill, and clinically it informs rehabilitation. Try to figure out where is the problem and how to fix it. So before we dive into the details, I'd like to step back and take a look at the larger picture of what our hands can do and where these complex skills come from. So evolutionary, there is this evolvement of the hand, brain, and cognition, and especially our ability of opposing our thumb. It's considered uniquely human, this pad-to-pad precision grip, and it's believed that this plays a critical role in the development of brain and cognition, even language. So it's such a huge complex, and in our hand encompass this enormous repertoire. So it seems to be a daunting task. Where do we even begin? And then researchers started with some taxonomy. So this is a classification first done by a British anthropologist Napier. He first made a distinction between prehensile movement, meaning closing all your fingers, and non-prehensile movement. That's anything that do not requires closing your fingers. And within prehensile movement, he also made the classification of power grip, that's making very strong grip, and precision grip. And then, of course, in everyday life, it's pretty much the combination of both. And here are a couple of examples of non-prehensile movement. And these are the vocabularies of American Sign Language. So how do we approach this big complex? Well, the first question stood out to us was this distinction between strength and finger control. It seems that there is this spectrum on two extremes. On the one extreme, you can make a very powerful grip, like rolling, but you lose fine control of each individual finger. But on the other hand, if you can precisely control each finger, but you cannot really exert that strong strength. Right? So our question is, do we always have to compromise one with the other? Or neurally, are they supported by two separate systems or not? And then the rehabilitation question then is, if we can improve finger individuation, because here in this study, which I'm just going to show you in a second, we use finger individuation as a proxy for fine finger control. And then if you dive into a little bit deeper, maybe that picture is a little overly simplistic. What about precision grip? So if you look at the neuroscience literature, there's this big two branches of literature used studying hand dexterity. One is using finger individuation, and another big chunk, especially in the non-human primate literature, people use precision grip. And these two are often treated as equivalent and interchangeable. But my question is this true? And rehabilitation question is, if we train one, does this transfer to another? Right. So that introduced my second question here today. I'm going to share with you today is, are finger individuation and complex manipulation operating on the same control mechanism or not? Specifically, I want to really dive a little bit deeper and look at what's the role of finger individuation in precision grip, and can we improve both, right? Okay, so the first one, are hand strength and control supported by separate system or not? This is a study, a longitudinal study done during my postdoc period at Johns Hopkins, and a quite large study directed by Dr. John Krakauer and Pablo Casals and Andy Love. It's called Study of Motor Learning and Acute Recovery Time Course of Stroke, SMART study. So we track patients for a whole year for 5 times, and from right after stroke to 1 year out. And we use several modalities, and data were collected at 3 sites, Johns Hopkins, Columbia University, and University of Zurich. So for this study, I'm going to focus on the finger control part. Again, this is just a reminder that our first picture at this dissociation or trade-off between power grip and individuation. Because there is this trade-off in pretty much all the tasks, there is a problem that you always need a little bit of strength to exert force. So how can we design a task or a paradigm to dissociate these two behaviors so that we can precisely control or measure the two components? So this is a way we come up with this way to take out the contribution of strength from the assessment of fine finger control. So this is a keyboard-like ergonomic device that people rest their hands on top of it. And underneath each key, there is a force transducers. We can track the isometric forces exerted by each finger. And then we have 2 tasks. Here are 2 screenshots of the tasks. One is the maximum force control. So we ask participants to push each of their finger as strong as possible. And here there's no requirement for keeping other fingers or just no instruction for other fingers. So this mimicking a strong grip. And then on this side is the finger individuation task. Here, calibrated to the maximum strength for each finger, we ask people to push at 4 different force levels, and they have to precisely match the force level. And the critical part is that they need to keep all the other fingers not moving. Right? So let me show you how we derive a measure to isolate finger individuation. Take out tease these 2 components apart. Right? So this is a healthy participants data. So force traces we record from during one trial. Here I ask them to push the 4th finger and try to keep other fingers not moving. And this is very small force at 20% for maximum force. And we can record how much forces we get from non-instructed fingers as a function of how much they push with this instructed finger. Right? So this is one data point, because we ask them to push at 4 different force levels. So this is another example. When they were asked to push at much higher level force, you see that other fingers start to co-activate more. So this is very intuitively straightforward. When we push harder, it's harder to keep other fingers not moving, right? So we can map out this relatively linear function. And here is another example of another healthy participants. So you can see the difference between the two. While this person were relatively weaker compared to this person, they were much better at keeping their fingers not moving. So we think that the slope of this function is a sensitive measure of people's ability to individuate their fingers. So to make it clear, here is an illustration. Right? So you can have two people at different strength levels, but they can have very similar individuation levels, like these two lines are parallel. So the extreme level of individuation is the flat line. The lower the slope, the better individuation. Okay? And here is much higher slope, so poorer individuation. To just be able to make it easier to compare to patients and also easier to do statistics, we take the negative log of the slope. So from now on, whenever I say individuation index, it's the negative log of the slope. Right? So with this tool, now we can track what's going on with patients during the recovery period. Right? So again, this is the timeline, and I'm going to show you again one patient's data just to see how things evolve over time. Right, so you can see at the very beginning, right after stroke, this is again the force traces. It shows that they were very weak, again trying to push the fourth finger and keeping other fingers not moving. So they were both very weak and also co-activated the fingers quite a lot. And then over time, the strength comes back, and also they become better keeping other fingers not moving. And the same phenomena get exaggerated when they were trying to push harder. So how does slope look like? So this is week 1, and 1 month, 3 months, 6 months, and 1 year out. Right, so this paradigm can really nice track the recovery processes, as you can see here. Right, both strength and the individuation. So as a summary, we tracked across all 3 centers over 50 patients and also 14 healthy controls. And you see an overall trend of recovery, and pretty much most of the recovery happened during the first 3 months. And what I'd like you to bring to your attention also is also this big gap between the impaired hand and healthy hands, even 1 year out. Right? And also we tracked clinical assessment. If you are curious, I'm happy to share more details offline. So our very question is, are these two, how do we answer that question, right? How are these two supported by separate system or not? To directly examine the trend of these two measures over the process of recovery, what I did is that I normalized both measures and put them into the space. And then normalization was done to the patient's non-impaired side. Right? So the same patient, I could normalize data and put them in the same space so that I can closely examine what's going on during the 1 year period. You can see a trend of moving from the lower left-hand corner to the right-hand corner. So when they get to 1, that means full recovery, right? And then this is the recovery space. And just to remind you that it's not causal link, right? So what I did first is to throw out all the data to this space, regardless of where we capture that during this whole year period. So each dot represents 1 patient's data. You see, so this is, again, this 1 patient. And then you see this is cashew nut kind of shape. That's our overall trend, right? So this is a static picture. What happened over time? So I have a little, all right, yeah, so and also tried to use a mathematical modeling approach to describe this this space, and turns out a piecewise linear function can best describe it. One thing really stood out is that there is this very high correlation before strength gets to about 0.6%. So it seems that there is a strength envelope, and after that, there's no correlation between individuation and the strength. And to show this evolvement over time, I have this little video, and each dot is one patient. You can see, and I illustrated 2 participants here. You can see this quite different improvement trend over time. And after 6 months, pretty much very little things was happening. Right? So without going into too much details, and if you're interested, I'm happy to talk more details in offline, that we use residual analysis and some mathematical approaches to show that there are 2 main recovery processes during this whole year period. So one is, as you saw, this main drive along strength and individuation initially, and mainly along strength later time period. And then, and on top of it, orthogonal to this main recovery function, and only along individuation dimension, there is also jittering early on after stroke. What's the neuron pathways to support this behavioral dissociation? So we, as I mentioned, we also collected tractography, DTI data. So we use a tractography analysis to look at this this question. So in the literature, I'd like to remind you that this is long been found using non-human primate studies to show that there is this direct pathway, corticospinal tract, more believed to be responsible for fine finger control, and that there is this non-direct pathway stop at brainstem, and starting from the mainly from the reticular formation within brainstem and then project to spinal cord. This is believed to mainly support the gross and strong movement. So we use this tractography approach, and we come up with a measure that you count how much of the volume is affected by stroke along these pathways. So this is a white matter tract, and here projected onto a healthy brain, the gray matter at the surface. So we use this affected volume measure and correlate with strength and individuation behavior measures, and showed consistently across time that individuation is more correlated with both gray matter and white matter of this pathway. So this concludes our first study that seems that strength and fine finger control are indeed supported by 2 separable biological systems. So it tells us a very important message to the rehabilitation field, that especially given that recovery happened mostly early on, so targeting fine finger control seems to be important early on after stroke. And there is also a very good news that if we can design tools to compensate strength for patients, that means we can allow patients to focus on their fine finger control recovery early on. And scientifically, that also directs us to dive deeper to the mechanisms of fine finger control, right? So to quickly look at how, if we can improve fine finger control. So this is just finished study. It's a pilot study. We trained patients with 18 patients, and with this finger coding task, is piano-like coding task. So we selected different combinations from 10 chords from the two finger combinations and the 3-finger combinations. And we're using the same device as the SMART study, and it's collaborated with my former colleagues, Firas Mawazi. And here, so we train patients for 5 days. Each day they come and to perform this task, and there are like about 400 trials. Takes about 4 hours each day, so quite intense training. And you see the difference. So this is the first day and an example of the force traces, and the second day. So you see that over time, patient could perform much cleaner separation of the fingers and keeping the instructed fingers at force, the required force level, and then keeping other fingers lower force levels, right? And then we also assessed their individuation and other clinical assessment. So we track them for 3 time points over 6 months period. So the nice good news is that with this small group of patients, we did see a very nice improvement of finger individuation over time. And also interestingly, the clinical assessment ERAT, which is pretty much a functional assessment of grasping object, we also saw improvement over time. And also intriguingly, the majority of recovery was the grip part. But now when I dive a little bit deeper, what's even more puzzling is that the improvement of individuation and improvement of ERAT were not correlated. And why, right? The question is why this is the case. So that introduced to my next question. Right? So this drives us to really dive deeper to these 2 main paradigms, individuation and precision grip. So I want to see like if these 2 are related or not, and are they supported by the same control mechanism or not? If so, or if not, and what's the role of finger individuation? Right. So this is our everyday life, how we use our hand in all these different tasks. So far, with the tools you have seen, right, pretty much the what we are doing in our lab. We have these are the tools I've been talking about, right? So we have the nice force transducers and track real-time, very good resolution of forces produced. And on the other hand, the clinical assessment is ecological, really much closer to everyday life and grasping. But the problem there is that it's very gross scale. We don't have nice resolution. And then here the problem is it's only a single dimension, right? So we've been thinking, how can we combine the advantage of these 2 tools and come up with a new device, a new paradigm? So that's what I've been doing in the past few years at Johns Hopkins with engineers in our lab and also in the engineering department. So this is the tool we designed. It has a extremely sensitive force sensors underneath each fingertip and can extract very small isometric forces in a near pelagic hand. And then another advantage is that it can track 3 dimensions forces. So let me just give you an example of how that works. So this is the very first thing with this nice tool I want to do is to look at the finger individuation now in 3D. Okay, so this is a screenshot again at the monitor, and with the forces projected to the monitor, and ask participants to control a little dot at the center of the space, and then try to hit the dot move the dot towards different directions, in all three directions, right? And all the other fingers they don't see, but that's they summed up with the red bar. Their goal is to try to keep the fingers not moving. So you can see here is an illustration. Right, so try to keep the red bars lower. So here are just two examples of the force traces we collected with this tool with the healthy participants and the patient. And it's very clear that from these force traces, you can see patients were weaker in certain dimensions. And the force direction seems to be a little off, right? So here another illustration of during one trial, how the force traces look like. So here, first the healthy participant, I asked them to control this dot. Each little dot represents one finger. The index finger, left hand index finger, try to hit this target. You see a very nice and clean trajectory, a little bit of activity recorded from all the other fingers, and the patient. The same instruction, but you see that patient not only get the direction wrong, they try to get towards that direction, and also a lot of co-activation from other fingers. Very different pattern compared to healthy participant. And with the same individuation measure as we did with the 1D assessment, we can now come up with an overall assessment of how well they can keep other fingers not moving. Right? So these are the data from a non-practice side. So that's their unaffected side. And then what about the affected side? Right, so I summed up with different anatomical directions. Again, if you are interested in the details, I'm happy to talk offline. So apparently, the flexion direction is less impaired, which was what was tracked by our earlier keyboard-like device. And the more impaired side are actually extension, try to open the fingers, and adduction, abduction, try to move fingers sideways. And the thumb is the least impaired component. Right? So maybe our speculation is that neurally we have the largest representation of the thumb. Okay? Again, as I mentioned, the question is, this is really a gross summed over all directions, exactly how each finger are individuating and then enslaving when the instructed fingers are moving. We went into deeper and then have fine analysis, but I'm not going to go into the details. I'm actually giving another talk at the neurocontrol of movement next week. So if you are interested, you can welcome to join. So the take-home message here is that the enslavement pattern in patient and healthy participants are qualitatively different. In enslavement pattern in patient can be explained by this lower level direction bias in their instructed finger, the active finger, whereas this is the enslavement pattern. Whereas in healthy controls, it's very hard because it's small value, but it's mainly driven by a top-down task demand, the instructed finger and target directions. But the main question for today I'd like to focus on is, what about precision grip, right? So again, I'm bringing back this little video clip again, but here the details is I'd like you to now watch it again, but look at exactly how he's using his fingers in his hand to grasp this object. And this is actually one of the pinch tasks in action research in the ARAT task. And also this patient had this canonical right internal capsule infarct, which is the part of the very critical part of the corticospinal tract. He was using his thumb and index finger to pinch this object, right? And now he turned this precision pinch into a gross movement. So to design a good pinch task, we were inspired quite a lot by the ARAT tasks. So very briefly showing you, this is again a screenshot of that task, and this is how the hand is set up within this device. So this is thumb to index pinch and thumb to middle finger pinch and thumb to the fourth finger pinch. So I'll focus on these three tasks. Okay, so to first test the validity of this tool, we tested the difference between healthy participants' dominant and non-dominant hand. We all know that the two hands are quite different in terms of the skill level, but exactly how? So let me show you again the force traces of the dominant hand gripping this object, and then the non-dominant hand. Again, these are all healthy and college students, so you see this huge difference between this the two hands. So how exactly we measure the performance? One way to do it is our main accuracy measure is the grip angle. So again, if you look at the force traces, the two fingers come close to the object. As you can feel that everyday life, when you try to grasp a small object, you try to bring the two fingers close to 180 degrees. Right? That's direct opposability, right? That's what we call thumb to finger, pad to pad opposability. So we think this is the critical part for fine finger control. So this is how we measure this angle. And across all three types of pinch, thumb to index, thumb to middle, and thumb to ring, and we show very strong difference between dominant and non-dominant hand. And then there are also other measures, right? We also look at how well they coordinate their two fingers in terms of the timing of when they reach to the object, and also the trajectory coordination, how the two fingers are coordinated during the whole trajectory, and the smoothness of the trajectory. Again, across the board, all these coordination measures where we see this big difference between non-dominant and dominant hand. So it looks like this is a really sensitive tool to capture this behavior. So now we can use this tool to directly compare individuation and precision grip. So the first look is with the same group of participants, all the healthy participants, we ask them to perform individuation, as I showed you before, and this precision grip task. And with all the measures, accuracy and also the coordination measures, there's no correlation. So this is really interesting. It looks like these two are not supported by, maybe they are really different. And if this is really different, then what is the role? Do we really need individuation in precision grip? And if so, when? So to go deeper, we designed a couple more tasks. So one is so exactly the same kind of pinch, but Now they are required to go through a tunnel. And we test for both tasks within the same group of participants, and we collected 17 of them. Yeah, so this is a tunnel task. And then another one is dial. So again, the same pinch, but now they are required to turn the object to a certain angle after the pinch. Okay, so now these two tasks requires people to really break out their synergy, and it requires their planning things a little bit ahead of time, right? So that's why besides grip angle, we also look at initial angle. So how the fingers start out and towards when they try to move the two fingers together towards the target. So this is initial angle. And again, the first look is to look at the correlation between the two, their people's individuation ability and how accurately they can do it. And across the board, all the tasks, there seems to be no correlation between individuation ability and the way they get to that final angle. And then there is a strong correlation with the individuation, with the initial angle. So this is very interesting, and we start to look at what's the role, why individuation now becomes important. And so we did, using linear mixed effect model, try to model the interaction of the task and individuation ability, and then there is a strong interaction here. So it seems that the individuation ability affects the planning of the simple pinch when the task really demands you to get out of the synergy in the object, the fine manipulation. And intriguingly, the direction is a negative correlation, which means the higher level of individuation, the less early planning people need, right? With poor individuation, people really start out early. So that's the first look. And then what about the trajectory quality? So what we focused on here is the smoothness. You can see that it is a huge difference across the tasks. So at the precision pinch part, the trajectory smoothness were about similar across the two tasks, but when people have to dial this part, the trajectory became a lot of a jerky. And now when we look at the correlation, again with a simple pinch, this is data I already showed, and no correlation. But once we get to the tunnel part, the people's ability of individuate their fingers strongly correlated with the jerkiness of their pinch trajectory. And then now in dial, the same thing, even though there is a huge difference during these two sections. So it seems that there are two components of trajectory jerkiness. One is that it's introduced by the task. So there's this main effect of a task on jerkiness. And then another is individuation ability induced jerkiness. There's a main effect here. And paradoxically, again, the higher the individuation level, the more jerkiness the trajectory is across all the tasks. So it seems that individuation ability introduces this extra level of jerkiness on top of the demand of the task when the non-synergistic movement is required. So seems that indeed these two, individuation and precision grip, or even larger in a larger picture, not only in precision grip but also fine object manipulation, really are operating on different control mechanisms. And exactly why and how, we are still looking at it. So what I shared, the data, was our first look. And stepping back of our picture of overall picture of dexterity, I'm thinking it's more like a tree instead of this two dichotomy. And hopefully it's a peach tree, and we have the strength component and the fine finger control component, and they overlap but largely distinct. And within control, we have individuation and other fine manipulation, also distinct but also overlap. So that's our conclusion. So as a conclusion, I have shown you that strength and individuation are largely supported by separate systems, and we can train to improve individuation. And when we dive deeper, look at the relationship between individuation and precision grip, it looks like these two are indeed operated by different control mechanisms. And exactly what's the role of individuation in precision grip and other complex manipulation, our first look shows that there seems to be a cost of individuation when the task requires non-synergistic manipulation. So that brings to the rehabilitation question: can we improve both individuation and precision grip? So that's what I'm going to do in my lab. Okay. So that's the end, and I'd like to thank the SMARTS team across Dr. John Krakauer and so Nick at Johns Hopkins led the team, and Dr. Jon Digersen and Navid helped a lot with the finger individuation task and device. And at Columbia University, Dr. Kitago and Heidi Schombrad helped a lot of the data collection and the stimulation part. And Zurich site, also Dr. Andy Loft. And the BLAMP lab led by Dr. John Krakauer and Adrian Hayes, and the members of the whole lab. And Kevin was the inventor of the 3D hand device. And also Tim and Sepna helped a lot with the data analysis, the data collection with the 3D device, and other members in the lab. And currently, I'm still collaborating with the Hammer Lab and led by Dr. Jeremy Brown at Johns Hopkins. And they are directing the development of this tool. And PhD student Jake Carducci is the main lead of this device development. And my very small evolving lab here, and also Brooklyn from Georgia Tech going to join us in September. So I'm very excited, and we are again seeking exciting research collaborations with your community, and very excited to join you and seeking talented trainees. If you're interested, please check out our website and email me. All right. Thank you.
Thank you, Jean. We already have a question from Shino. If you'd like to go ahead and ask that by unmuting.
Yes, so thank you very much for the interesting presentation. So then I've done this similar kind of study a long time ago, and then this I'm curious about what you're looking at in the individuation, whether it is a natural individuation or maximal capability for individuation. So my question is, were the subjects asked to maximally individuate, meaning not involving other fingers in the direction that is required, or were they just instructed on the main fingers and just to forget about other fingers?
Which task were you
All
referring
of them,
to?
because you're trying to integrate all the findings. So depending on the task requirement, I think it'll be different. I mean, we need to be careful about integrating the findings.
Yeah, exactly. So this the individuation task, we really stress keeping all the other fingers not moving. That's why we have the red bar over there and ask them try to minimize that red bar. So they need to monitor that. The same thing with our very early task that they see all the force traces from the not force traces but the little white bars represent the force exerted by all the fingers, so they can monitor it. And then the task really specifically asks them to keep other fingers not moving. So that's only in the individuation task. And then in the precision grip task, we didn't give any instruction about other fingers. That's the interesting part, like to look at the interaction of individuation ability overall, right? And the way people perform these tasks. In everyday
Right.
life,
Yeah.
we
Hmm.
don't, right?
Hmm.
I mean, when we grasp things, we don't think about individuating other fingers, right? I mean, keeping other fingers not moving.
Right. So naturally, we don't think about it, but experimentally, because we are imposing another task actually. So it is, it involves both the divided attention and other things. So that actually in the last one, I was curious because you mentioned the better individuation will have greater jerk. So it could be that they try to distribute attention time to time to other fingers to try to maximize individuation, then that you might lose the control. I mean, to the the task fingers, so that at that point there could be some jerk happening.
Yeah, so I'm thinking that because the task now demands they really have to precisely
Hmm.
control the fingers,
Hmm.
there is this cost coming online.
Right. So it's like a multitask, condition in a way. So yeah. So
In,
you know,
in a
I just
way.
stop here probably. Yeah. Thank you. We'll talk later individually.
Yeah, sure. Yeah,
Hmm. See you then.
yeah, thank you. Yeah.
If you have questions, just say you do in the chat, and I can call on you. But in the meantime, Jing, it was interesting. You were saying that people who have less individuation have to plan a lot earlier. I'm wondering if you tested that. Since you have this nice device, can you design a task that is in alignment with the directions that they naturally produce and show that that's easier for them?
So right. So actually, in our task, the tunnel we give them is aligned with their natural direction.
Oh, okay, gotcha.
Right. But the difficult part is that if they hit any of the walls, they have to start over again. So the requirement is really to keep the more straight direction. It's like when you have to go and poke into a hole, right?
I
And
also want.
the
Yeah, go ahead.
yeah, go ahead. Yeah, so that actually reminds me of also another issue. So not issue, the interesting point. So it is isometric task, right? So
Yeah,
isometric task for the one direction, but in reality, you move your finger when you pick something, so that the
yeah,
direction of force would change,
yeah.
when you move. So how would you consider that?
You mean the direction of the
Mm,
force? We can
mhm.
with 3D we can actually clearly see that they with the force traces.
Well, I guess
Right, right,
the
right, right.
question is like,
Yeah. Mm, mm,
since the fingers
Right,
aren't actually
mm,
moving all the way
mm.
close to each other, their directions might change, or
right.
do
Let
those
me
points move in space?
Mhm.
Yeah, so this shows you how the trajectory, like the point move in the space, right?
Right, but the finger
The
is in
fingertip, the
static.
fingertips.
Yeah.
Yeah, the fingers are not moving, but the forces, you can see exactly like which direction it's moving.
Yeah, so that
Yes,
might
but
change
yeah.
when you are moving your fingers, right? So is there a way to make that your task even more kind of ecological where you actually cause the movement of the fingers to close?
Right, yeah,
Because
yeah. I mean,
the
that's a very
ability to
good
make the
question.
force out here is different than here, right?
Right. Maybe a glove, right? And then that's why I'm also interested in the DLC. Right. So with other tools, making it really more ecological is to get the hand out of the device, maybe. Within the device, we think well, there are some studies really, I guess, Lena, you are also part of it. You look at if the control of isometric forces in the space, can that transfer to the control in real space? It seems to be a lot of things can directly transfer. Right, that's why we think the isometric tool is still a very useful tool to look at these control abilities.
I'm wondering if you just change the initial posture too, so you could do one test out here and then another one like that.
Yeah, sorry, I can't see you here.
Oh, sorry. I see me on the bottom of the screen. But anyway, just you could do an isometric test with the fingertips closer to being together. You're kind of like this. So maybe if you also did the test closer like this, that might give you some insight into what happens as you kind of get closer to the target in
Right,
terms of
right. So
biomechanics of your hand.
yeah, that's a very good idea. Right now, pretty much all the setup is the most natural, most comfortable posture that we have a setup step that it just requires them to relax all the fingers, so we record close to zero force. That's their starting posture. Yeah. So yeah, definitely, if they start out with different postures, I'm sure that will affect the performance and how they plan out, right? Yeah.
Are there any other questions? I was watching the movies that you had in the beginning with the kind of tracking people over time with their individuation or various things. Um, it seems like if you look at the end point, it looks like they're all getting better, but in the middle, were there people going backwards? And do you think that's real, or was that just kind of non-repeatability of the test?
Yeah, I don't think that's real, but it is possible. There's some patients had a reverse, but I don't think we can tell from this data set really it is phenomena or not. And also we only collected 5 time points, and everything in between are just like I did modeling to fill out the gap, so to make the whole movie smooth. But it's just the spline modeling in between. Yeah. I think the movie right now can tell is the overall trajectory, the trend of the whole group. Yeah.
Right. Okay. Well, we're actually just 1 minute over time, so I want to thank you for joining us again, and please reach out to Jing if you're interested in collaborating. And thanks, everyone. I guess we have one more GT Neuro Talk next week.